All right. Welcome, everybody, to this week's Science Assembly. Let me get my slides up here. Okay. Zoom wants to do things. Okay, here we go. All right. Hopefully everybody can see these slides okay. All right. Well, welcome to this week's Rubin Science Assembly. For those of you who don't know me, my name is Sarah Greenstreet. And today we are going to be walking through a new tutorial notebook that I put together on interactive catalog visualization using some advanced plotting techniques. But before we get there, let's see, can I advance my slides? There we go. Okay, so we have a couple announcements to run through. Actually, there's quite a few this time. There's a lot of things, again, either getting toward the end of the year or we're just ramping up with lots of exciting things for Rubin. So there's lots of stuff that's been happening lately to tell you about. And then we're going to run through the tutorial. Just as a heads up, this is the name of the tutorial notebook we're going to be going through. It's called DP0.3 07 interactive catalog visualization. And the link here for where you can find that on GitHub is on here as well. Let's see, let me stop sharing and then I can put the link to, where did my slides go? Oh, there they are. Okay, sorry, I'm losing everything here. I want the link to the slides and I will put that in the chat so everybody can get to these slides that I'm sharing. So this has the links to the slides here and to where this notebook is. Okay, we're getting organized here somewhere. Okay, so the GitHub link for where this notebook can be found is the second link here, and the name of the tutorial notebook that we're going to be going through is the top one. Okay, so let's get through the announcements. Hopefully we'll have a little bit of time for some questions at the end. I'll try to stop at a couple places as we're going through the notebook to take some questions if there are some. It's pretty long and dense, so we'll try to get as far as we can through it before the end of the hour. Okay, so on to some of the announcements. First thing up, we now have dates for when the next Rubin Community Workshop will be happening. It's going to be the week of July 28th to August 1st. It's going to be in Tucson this year. It will be fully hybrid. In-person attendance is going to be limited to 250 people, which is, I think, the usual limit for in-person participation. But it is fully hybrid, so if you can't come in person, you'll be able to attend virtually. There aren't a whole lot of details yet about the meeting that are specifically set up yet, but the website will get set up probably early next year sometime, and more details will come out when registration opens as well. But you can at least save the date for now, that it will be the last week of July into the start of August when the next Rubin Community Workshop will be happening. I hope all of you have been keeping up on what's been going on with the ComCam commissioning. There's been a lot of exciting things going on. There have been updates that have been getting posted to the community forum weekly, just to keep the community up to date on everything that's been going on. The latest update, there's a link here in the slide as well to that latest update. All of the information that is in these updates that get put on the forum are public. And so you're welcome to share that with anyone you want. If you want to post those things on social media, you're more than welcome to do that as well. There's also an interim report on how the ComCam on Sky campaign has been going. There's a link here. It's the Sitcom Tech Note 149. That I think this is the one that was just put together by the commissioning team. So you can also take a look at that if you want to see some of the details of what's been happening with ComCam and commissioning. Another thing that I went ahead and put on here, I know this has been talked about at some of the past science assemblies, There is a pretty cool news story, a press release that was put out by Rubin Observatory once we actually started looking at the sky with ComCam as well. So the link to that story is on there if you also want to see it. And then we also wanted to draw everyone's attention to some of the job openings with Rubin. There's a community scientist that will be a position held in Chile that's going to be advertised soon. If you want to know more about that before the advertisement comes out, you can contact Melissa Graham. Her email address is here. And there's also a link down here for all of the open jobs that are currently open for Rubin Observatory as well. So feel free to pass those on to students or colleagues or anyone else that you might think would be interested, or check them out if you yourself are interested as well. Few more announcements, some regarding the Rubin Science platform and Data Preview 0. The latest recommended image of the LSST science pipelines was updated on November 1st to the weekly 42 version. So that's the version that we recommend people use when they're on the Rubin Science platform. We've had a couple updates to some of our tutorial notebooks. Two of the DP0.2 notebooks, notebook 03C and 13A. 03C is on the Big Deep COAD cutouts, and 13A is on the image cutout science demo, have had some updates to them recently as well, to kind of add some extra functionality in there as well. And then there's the new DP0.3 tutorial notebook number 7, which we're going to go over today, that was released on November 22nd as well. So one new notebook and a couple updates to some of the old notebooks. And then finally, the LSST Survey Cadence and Optimization Committee released its Phase 3 recommendations, which came out in this Project Science Tech Note 56. And there's a link here if you want to go look at all the details of that. I believe this is the final recommendation for the survey cadence that's going to be coming out of the SCOC before we actually start the science observing at some point here in the near future. So if you want to take a look at that tech note, the link is here, and there's also a community post about some of the things that are different or updated in this Phase 3 recommendation compared to the Phase 2 recommendation too, if you want to look at that. Okay. Also, as at every science assembly, we just want to remind you all that if you have feedback about either the Rubin data products or the Rubin science platform, that the Rubin Users Committee is the best resource for you to go through with providing that feedback. So there's a link down here, kind of toward the bottom of the slide, with a Google form where you can submit any specific feedback that you have about the Rubin data products or science platform. And the Users Committee takes all of that information from the community, which is what their charge is to do, is to receive that community feedback. And then they write reports twice a year that go directly to the Rubin Operations Director. So it's a great way, if you have specific feedback or any concerns, to be able to funnel that all the way up to the top of the command chain, and we'll try to make sure that all that can get addressed in one way or another, and hopefully accommodated as well. So please use that resource because they're a great resource. Okay, and then finally, I just wanted to go over the schedule for the upcoming Science Assembly since we're getting to the end of the year here. You can always find the schedule at dp0.lsst.io. So after we go through the tutorial for today's Science Assembly, we are going to take a 3-week winter break from the Science Assemblies as we get through the end of the year with the holidays. And then we'll be coming back on January 9th for a tutorial that will be led by Yumi Choi on how to join user-uploaded tables in the Rubin Science platform. And then we're going to continue alternating back and forth between tutorial weeks and drop-in Q&A sessions. And then again, on the 23rd of January, there's going to be a special presentation by Melissa Graham that will kind of go over a review of Data Preview 0 as we're kind of wrapping up using Data Preview 0. There'll be some celebrations and thank yous for all of the delegates. We've really appreciated all of the efforts that you have put in with coming to these tutorials and using the Rubin Science platform and all of Data Preview 0. And so please plan to come to that presentation by Melissa. And so we're kind of wrapping up DP0 and looking toward Data Preview 1 that's going to be coming soon. So on February 6th, we will have another tutorial presentation that's going to be about looking forward toward Data Preview 1 coming early next year as well. So please stay tuned for those tutorials coming up, and please plan to come to as many as you can as well. Okay, so I think that is everything for the announcements. It's kind of a lot this time. Is there anything that anyone else wants to add or any questions about any of that before we move on? Okay, I don't see any hands. So, all right. I am going to, let's see, let's escape out of here. Okay, so if you would like to follow along in what we're going to be doing here with the tutorial, which you are highly encouraged to do, then you can go to the Rubin Science platform at data.lsst.cloud. I think most people here have probably done this before. You can then sign in to your account on the top right-hand corner up here. And once you are signed in, we're then going to go to the notebook aspect of the Rubin Science platform. So you can click on notebooks. On the left, you'll see the list of the possible images of the LSST science pipelines. We're going to choose the recommended weekly 42 version of the pipelines. And then today, for the option of how large of a server we're going to choose, we want a large server because we are going to have a large data set with lots of complicated interactive plots that we're going to be playing around with. So go ahead and choose a large server. And then we'll let this spin up for us. Sometimes with a larger server, it takes just a little bit longer than the slightly smaller servers, but hopefully it doesn't take too long for anyone. And so then once this starts up, this should put us right into the notebook aspect of the Rubin Science platform. And from there, we'll be able to get right to, here, let me close this, right to the notebook that we want to look at today. So once this server spins up for you and you're then in Jupyter Lab, you can go to your home directory and under my notebooks and tutorial notebooks, all the way at the bottom of the list here, all of the DP0.2 tutorial notebooks appear farther up on the list, and then DP0.3 are at the bottom. We're going to choose the last one here, the DP03 07. That's the interactive catalog visualizations. So hopefully everyone is able to find this okay. Is there anyone that is having trouble being able to open this notebook that would like to run it and follow along with what we're doing?
I have to clone the director, or I have to clone the repo.
Okay.
Yeah. So anyway, but I know what I'm doing. So I was just, if anybody else had that issue, I just want to let you know.
Okay. Great. You might have to do a git pull as well if you already have some of the notebooks in here and just need to pull in the rest of them. This notebook only showed up a couple weeks ago as well. So that may be another way to be able to make sure that you can actually see this notebook. Okay, so the first thing that we are going to do before I start walking through this whole notebook is that I want everybody who's following along to scroll down with me because we are going to, oh, here, sorry, let me restart my kernel and clear all my outputs. This is partly run from yesterday. Okay, so we're gonna scroll down. We're gonna get past section 1 here, past some of these function calls, and I want you to scroll down once we get to section 2 that says use the tap service to obtain table data. And this is where you'll see we're gonna run our query. And I want you to scroll below the query where we actually run the query, and I want you to select the cell that just has unique MBAs in the cell. That's the only thing that's in the cell. This is going to be displaying the pandas data table that has all of the results of our query in it at the end. So I want you to select this cell, and then we're going to go up to the menu on the top left-hand corner and select kernel. And then I want you to go down to restart kernel and run up to selected cell. We're going to select this, and then what it's going to do is it's going to run all of the cells sequentially in the notebook up until it gets to this selected cell, and then it's going to stop for us. I want it to be doing this in the background while I go back through and tell you what this notebook is about, because this query takes about 6 to 7 minutes to run. And so I'd rather be talking while that query is happening so that by the time we get to this part of the notebook, the query is hopefully already completed for us. So this will kind of help us out and speed things up a little bit for us. So make sure that you have this unique MBA cell selected. And then under kernel, choose restart kernel and run up to selected cell. So I'm going to select that. It's going to ask if I really want to restart the kernel. So I'm going to say yes, select restart, the red button. And then you see that it's now going to be processing all of these cells up until this one, but it's not going to go past this point. Okay, so now we're going to scroll back up here, and I'll do my little intro about this notebook and what we're going to be doing today while this is running in the background. Okay, so this notebook is looking at the simulated solar system object catalogs from DP0.3. And showing you how to do some interactive visualizations for those catalogs using 3 open source Python libraries. These libraries are HoloViews, Bokeh, and Datashader. This notebook is very heavily adapted from the DP0.2 Notebook 06B that was developed by Leanne Guy. I believe it's been well over a year since this notebook has been out, probably longer than that. So this version of the notebook was adapting her notebook for DP0.2 to the DP0.3 simulated solar system catalogs. So it's very similar to that notebook, but kind of adapted and extended for this different data set as well. So one of the great things about the Rubin Science platform is that it allows us to be able to have these huge, unprecedentedly large and complex data sets that are going to be coming out of LSST and be able to do scientific analysis on those. But we may also want often to be able to do some visualizations for these very large data sets. And there are some techniques and software libraries that are available that not all astronomers are very familiar with. And so that's why Leanne had put together the original DP0.2 notebook, and then also why we wanted to be able to adapt this for the solar system catalogs as well. So this notebook walks us through these 3 different open source Python libraries that enable this powerful interactive visualization of catalogs. So these 3 libraries are HoloViews. HoloViews allows you to produce high quality interactive visualizations that you can very easily annotate your plots with directly in how you set up the parameters for the plot. Without needing to call these additional plotting libraries as well. Bokeh is kind of a plotting backend for HoloViews that allows you to do data visualization with interactive tools such as brushing and linking between multiple plots. So we're going to talk about what those two things are. But they're really nice for being able to interact with these plots and even manipulate multiple plots at once. And then the third one is data shader, which is really good at accurately rendering really large data sets very flexibly and quickly as well. So that's at the very end. We may have to skip over some things at the end as we get down here and skip to the data shader part because I want to make sure that I can show you that as well. Okay, so that's kind of the introduction to these different libraries that we're going to be walking through how to use. These were new libraries to me when I started putting together this notebook, but it was really fun getting to play around with all of the abilities that these tools have. Okay, so first we're going to start with importing all of our packages that we need. There's lots of different functions within these different libraries that we're going to need. We don't have to rerun these cells now because we're already running these ones at the top of our notebook so far. This just shows you how to print out the versions of each of these different libraries in case you want to know what version you're looking at or working with. We'll set the maximum number of rows that are going to be displayed in our pandas data tables to 5, just to make sure that we don't have too big of a notebook that's holding too much memory. There's a note here about making sure that these next 2 cells are run in the following order, which is just making sure that all of the Bokeh plots get output to this notebook. So that's where they're going to be displayed. And that Bokeh is the plotting library backend that we're going to use for HoloViews. So this cell here is just setting that HoloViews plotting extension to the Bokeh library. And then there's a couple different cells here as well that have some information for making sure that, again, the plots are going to be output to this notebook so we can see them within the notebook itself. And there's also an option down here farther that we probably won't get to today for being able to output some of the plots to an interactive HTML file that you can pull up in the browser and interact with that way as well. So this is just setting up things in a nice, correct way where you're not going to get any errors farther down. Okay, then we have a couple functions that we're going to define in order to compute some additional orbital elements for our solar system objects that are not included in the simulated data tables. So one is to calculate the semi-major axis, and one is to calculate the aphelion distance. So we're going to make sure that we've got those defined up here as well. Okay, and then we get down here to actually doing the query from the TAP service. So for the solar system simulated catalogs, we have a separate solar system object TAP. So we need to make sure that we use the SSO TAP service here for setting up our query. And then here is the conditions for the query itself. So for this notebook, we are going to be focused on main belt asteroids and just the main belt asteroids for all of these plotting examples. So here I have set up some of the bounds for the main belt objects that we want to restrict our query to. So we only want things with a semi-major axis between 1.8 and 3.7 AU, which is where the main belt is. We are going to do a minimum perihelion distance of 1.3 AU. So we're going to cut out all of the NEOs because we don't want them in here. We're just going to restrict to the main belt asteroids, and eccentricities no larger than 1. We don't want things that are unbound from the solar system. And then for our query, we are going to select each of these different parameters within 2 of the different data tables. So we want the names and some of the orbital elements for these objects. We also want some of the observational information, such as the arc length and the number of observations, and the magnitudes in several of these different bands as well. So we're going to pull these from the MPC orb catalog, and then we're going to do an inner join on the SS object catalog, since these 2 catalogs have the information we want to pull out. We're going to join them on the SS object ID, which is common between these 2 catalogs. And then we want to make sure that we're restricting the objects that come out of the query to these orbital element parameters that we've defined at the top of the cell. So this is just setting up what the query is going to look like. And then the cell below this actually runs the query. And you can see this one just finished for me. It took 7 minutes and 15 seconds, which is apparently how long I've been talking, trying to get through to this point within the notebook. Okay, so the query has finished, but now it's putting all of the query results into a pandas table for us that we're calling unique MBAs. And so this is taking quite a long time because we actually have over 4 million main belt asteroids that are going to be coming out in this query. And so there's quite a lot of objects. It's trying to get them all put into the table. So once these two cells finish executing, it will actually show us a preview of what that data table looks like and everything that's in it, and tell us how many objects are in that table. Okay, so while that's still running, let's go ahead and start walking through these next cells as well. So these next two are going to calculate the semi-major axis of all of the objects in our unique MBAs table, and it's going to add the semi-major axis as a new column to the data table as well. So let's go ahead and run. Okay, so this just finished for me with the pandas data table being put together from our query. So you can see here that we've got just about 4.25 million rows in this data table. There's a lot of main belt asteroids. And we've got all of the different parameters that we had put into our query as well are in this table now. Okay, so let's go ahead and compute the semi-major axis. We'll run this cell and the aphelion distance as well. And we're going to add both of those as additional columns to our table. Let's see, I just saw something pop up. Yes, okay. Same thing for Tim then. 7 minutes to get the query done, and then about 2 minutes for actually doing the pandification. I like that word. Okay. All right. So next we've got some additional information that I wanted us to add to our data table as well. So here we're going to split the main belt asteroids in our table up into different dynamical classes. Here where we're doing just simple semi-major axis cuts within our semi-major axis range of 1.8 to 3.7 AU. So here we're going to define the conditions for each of these different dynamical classes with these cuts on semi-major axis. And then below this, we're going to define what the names of these populations are. So this is the name for the conditions that we've set up above. So we're mapping some kind of label to the conditions that we set up here. And so these have to be in the same order as you define them. So the first one that's listed here is Hungaria. So these are the objects that are at the top of our conditions here that have semi-major axes between 1.8 AU and just under 2.0 AU. Then we have the inner belt objects, the middle belt objects, the outer belt objects, and then the Cybele are on the outer edge of the main belt. So this is just putting the names to go with those conditions that we're defining. And then we need to actually put this information as a new column in our data table. So that's what this cell here does. We're going to call this new column MBA pop for the population that each of these objects go into. And so here we've now displayed our unique MBA's data table again. And if we scroll over to the right, you see we've now added our semi-major axis and aphelion distances for each object. And we have this MBA pop column that also is telling us which of the different dynamical populations within the main belt these objects belong to. Okay, You can also just output how many objects are in each of these different populations. This is also a way to check to make sure that every object went into one of these different populations, and that sometimes if you have an other column listed here with any objects in it, it means that they kind of fell through the cracks in your definitions for trying to define things. So those are things that couldn't actually go into any of the categories, but it looks like we've covered our semi-major axis range well with our definition. Okay, so moving on to some of the visualizations. The first visualization is a very simplified visualization, but I learned how to do this. So this is putting all of the objects in our MBA table that are defined by their populations into a pie chart. And so I'll go ahead and execute this cell here. I know we don't often use pie charts as astronomers, but I saw an example of how to actually make this. And so I figured I would include it in this notebook if anybody ever wants to make a pie chart about different populations within the solar system. Here's an example of how you can do that. So you can see that the Hungarians and the Sibylles, and if we hover over this, it actually tells us how many objects are in that part of the population. That the Hungarians and Sibylles are a very small part of the main belt, and the inner, middle, and outer belt populations roughly each make up about a third of the main belt population. Okay, no big surprises there, but maybe kind of cool to be able to plot a pie chart. Okay, so one more thing that we're going to add, one more piece of information we're going to add to our unique MBA's data table are 3 different colors that we're going to compute from some of the apparent magnitudes. So we're going to do G minus I, R minus I, and G minus R using these apparent magnitudes from our table. So if we execute this cell, we print out our unique MBA's table again. And if we scroll over to the right, you can see that those colors are now added as columns here. Some of them have nan values because some of the apparent magnitudes themselves that go into those colors are actually nans. So there were not magnitudes collected in this simulation for some of these different band passes. And so, of course, the colors can't actually, don't actually make sense. But that's okay. We've got our colors in here. A lot of these objects have the full colors, so we can use those colors for making some of our plots farther along here. Okay, so that's a lot of setup, but we now have all of the data that we want to be able to use now for making some of our plots to visualize what this data actually looks like. So the first of these packages that we're going to walk through is HoloViews. Actually, before I do that, I should pause and ask if there are any questions. I didn't see any more chats pop up. Did anybody else have any questions about any of the setup piece? Okay, I see no hands, so I will keep going. Okay, so HoloViews is one of these packages that allows you to easily visualize large data sets. We are actually going to, because we have over 4 million objects in our unique MBA's table, so that we're not using that many objects for all of these plots, we're actually going to cut it down to just about 20,000 objects in our table for most of what we're going to show here. It'll help the notebook run a little bit faster with not having quite so many objects, and they won't be so overplotted as well. So this cell is going to actually get a random sample of our unique MBA's objects and put them into a data table that we're going to call data20k underscore MBAs. And so then this is the data table that we're going to use for most of these plots. So if we execute this, you can see we're now printing out the length here. We've got just over 20,000 objects in this smaller 20k MBA's data table. And so these are what we're going to use for a lot of these different plots here. Okay, so the way that these plotting libraries work is different from some of the other plotting libraries. There was a lot of kind of a bit of a steep learning curve for me as I was putting together this notebook, because I'm not familiar with the ways that these plotting libraries will set up plots for you. So there's some descriptions within this notebook that kind of try to help walk you through the information. There's also lots of really great resources. All of these different links within this notebook as well will take you to web pages that explain in much more detail how these different plotting packages work and the different pieces that you set up within these plotting packages to do things here. So there's a lot more information that you can go and look at if you would like to go deeper into an understanding of what these things are and how they work. But the basic core primitives of HoloViews are called elements. And so elements are these wrappers that let you be able to make these visual representations. So things like a scatter plot, a scatter element, is one way that you can make a scatter plot within HoloViews. And so we're going to start by doing some scatter plots using the HoloViews scatter element. Also, in order to be able to choose the columns that you want to plot, instead of actually just subsetting the data, HoloViews lets you actually specify the dimensionality directly. And so KDIMs and VDIMs are basically like your x-axis column, the information you want to plot on the x-axis, and VDIMs is what you're going to plot on the y-axis. And even though we specify them as strings, they are actually rich objects. So you can put a lot of information into these different dimensionalities as you're building up the different pieces for your plot. And I apologize if I'm not explaining this very well. It's still something I'm trying to wrap my head around exactly how it works. But everything in this notebook does work the way that it's set up. And so it's at least an example for you to be able to understand how to successfully use these different libraries. And as I said, there's lots of information on the websites for each of these different packages for understanding why they work the way they work if you want to go through and understand that better. Okay, so the first thing that we're going to do here is we are going to create a simple scatter plot that we're going to call AE plot. It's the HoloViews scatter element here. We're going to use our data 20K MBA's pandas table, and we're going to define our two different dimensionality units, our KDIMs and VDIMs here as the semi-major axis values from our data table and the eccentricity values here. So we're going to plot semi-major axis versus eccentricity in this AE plot. These different elements also have options that you can define, such as the axes limits, how big you want the plot to actually be, and the scale for your font, all of that normal kind of plotting optional information. And here we're going to choose to actually not show the toolbar in this first simple version of the plot. So this cell just makes the plot element for us. It doesn't actually show it. It doesn't display it. So here in this next plot where we just call this, this plotting object, it will display our plot for us here. So this is semi-major axis versus eccentricity. As you can see with the main belt, you can zoom in and out here with your mouse if you so desire as well, but it's a pretty simplified plot. Okay, so moving on, I realize we're getting toward the end of the hour and we haven't done very many of these plots yet. So I apologize for trying to spend so much time setting this up. Okay, so we can do a second plot as well. Here we're going to do a histogram of the H magnitude distribution for the objects in our 20,000 MBA's data table. So here we're setting up the plot again, and now we're displaying this plot. here we've now not chosen to remove the toolbar. So we have a toolbar on the right-hand side here. And the toolbar allows you to do different interactive things with the plot. So the little magnifying glass with the little scroll bar thing here is the wheel zoom. So when this is selected, there's a little blue bar here. That's when you can use your mouse pad to be able to zoom in and out. If you deselect this, it no longer zooms in and out using your mouse. And there's also a zoom feature as well. So you can draw a little zoom box, and when you when you select your region and let go, it will then zoom in on that region that you selected. And then there's a little reset button on here as well. That's kind of an introduction to what these different toolbars will do within these plots. Okay, so layouts of unlinked plots. So you can actually connect different plots together to plot two different things side by side as one plotting element, basically. So this is called a layout, which is kind of like a container that will put different HoloViews objects together into one layout. And so here we have our H distribution plot. That's the H magnitude histogram. We can also add some additional options for our AE plot that we defined above. And then here we can actually put these two things together. So if you have two different plot objects, you can actually connect them with a plus sign and make another plotting object that has both of those two plots together. So if we run this cell and the next one that will display this, you can now see that we have two different plots here. And one of the things that we added to the AE plot, an additional tool, is the hover tool. So you'll notice as I hover over the plot here, let's see if I can get just a single point together to highlight. So this will give you the semi-major axis and eccentricity value for this specific object that's beneath the cursor here. So when we're in the middle of this dense blob, there's lots of objects, and so the AE values for all of those objects are listed here as well. And there's still options to be able to zoom in on things. When you do one thing to one plot, it doesn't actually do anything to the other, but you can see them both at the same time and then reset them again. Okay, so that's two plots that are together in one connected layout, but they're not actually linked to each other. So the next thing we're going to do is talk about these layouts of linked plots where the two plots are in fact actually linked to each other. So here are some different options for setting the customizations that are used for the plotting styles. So if we just want to make sure that all of our plots follow a similar plotting style, we can define these here. This one is for the bokeh customizations. You can also, if you don't want to use bokeh as your plot style, you could use matplotlib as well. So we can set an additional plot style to be matplotlib. And then we need to pick which one we want to use. So here we're going to use the bokeh plot style. So if you run through this notebook and then want to go back through and do it in the matplotlib style to see how that's different, that's something that you would be able to do as well. Okay, so let's also next look at a color diagram for our 20,000 MBAs in our data table. So we can set the axes as rich objects within our HoloViews plotting objects. And so we can set the dimension for one of our axes as the R-I colors. We can even give it a label and a range, and same thing for G-R. So we're going to define these axes, and then we're going to create a color scatter plot that's very similar to what we had above here with our scatter element and this 20K MBA's data table. And then we also, on top of having the scatter plot, we want to be able to do a two-dimensional histogram distribution along the two different axes for our color diagram as well. So that's setting up this histogram as well that's going to be plotted on top of our scatter plot. So if we execute this color plotting object cell here, we see that we've now got our color diagram. And as it's hard to see because there are so many points in here, that it just looks like one giant blob. But what the histograms do is kind of show us that there is actually these two different color distributions that are within here in both the G-R and the R-I values. If we zoom in, you can see that a little bit better here, that there are in fact these two different peaks in the distribution as well. But this just gives you additional information. Okay, so that's one of our plots as well. For bokeh, so you can use bokeh to be able to do, as I mentioned at the start, data brushing and data linking as well within bokeh, which is one of these backends for HoloViews. So data brushing is where when you manipulate the data in one plot, it will actually also synchronously manipulate the data in the other plot, which you can do when you have those plots linked together. So that's what we're going to try to do here with these next few plots. Now, again, there's lots of different pieces here with how to set up these plots that might be different than what you're normally used to. So this next piece is using what bokeh calls column data source, or CDS objects, I suppose, where here you're basically taking the data from the various columns within your data table, and we're going to package them in a way so that the plotting package can then source that data in an easy way to be able to display it for you. So it's basically a dictionary where you're taking each of the different columns, or any of the columns that you want within your data table, and defining them as different variables within this dictionary that you're then going to use as the data for your column data source object that bokeh will use for visualizing things. And again, I apologize if I'm not explaining this in a very clear way. But this is setting up, this is how you create one of these column data source objects using some of the information from your data table. So we'll go ahead and execute this cell. If at some time later you realize, oh, I also want to be able to have this information included as a source for what I'm plotting, this is a way to be able to add additional information to that same dictionary. Okay, let's see. So an additional thing we can do that is kind of cool for making plots is be able to change the size of the point that you're plotting based on a given parameter. So here I'm showing an example of plotting the point size based on the H magnitude for an object. So like we did when we set up our conditions for the different dynamical populations, this is the conditions for how I am splitting up all of the different H mags into different categories. And then this is the point size, the data point size for our plot that we're assigning to each of those different H magnitude conditions, so that we can then add this variable point size based on H magnitude as another part of our source data that we can use within our plots here. And then we can create something called a points view using this CDS that we've now created. So all of the data is in here in a way that we can now use to be able to make these linked plots where we can do the data brushing between them as well. So we're still trying to set things up. There's a lot of different setup pieces here. This will set up the hover tools for the two different plots that you're going to link. So you can use all of the information that we just put into this column data source object as information that we'll use in our hover tool. So we have to define it both for the left plot and the right plot here. And then we're going to make our plot. So we make the left side plot, which is going to be semi-major axis versus inclination. I'm going to try to speed up a little bit as we're running out of time. And then we're going to do the right-hand plot, which is a color plot as well. So this is all very similar to what we did up at the top here. And then we're actually going to display this plot here. So now we've got our two different plots here. You can see if we do our hover tool now, these are all of the different information from the columns within our data table that we put into this column source data that we can now use in our hover tool to be able to highlight this information for any of the objects in our plot. So we've got the MPC designation, which population this object is in, its orbital elements and H magnitude, its apparent magnitudes and its colors for all of these objects. And of course, if you hover over a very dense part of the plot, you get that information for every one of those plots. Points that you're hovered over top of. Another thing you can see here is that as I am hovering over an object on the left-hand side, it shows up as a red dot on the right-hand side. This is part of the linking between these two plots. So now you know not only its semi-major axis and inclination based on this plot, you know all the other information that shows up within the hover tool information, and you know its location on the right-hand plot on the color plot as well, which again is in the hover tool information, but it shows you in a visual way. You can also zoom in on things here. And there is, let's see, if you select things with the box that doesn't have the magnifying glass, you can select a region on one of the two plots, and it will actually show you on the right-hand side where all of those objects go. So the things that weren't selected in your box are kind of dimmed into the background. And if you don't want to do a box section, you can actually use this little lasso feature for selecting an area as well, and it will show you the difference between the two different plots. So now we're starting to get into, there's a lot of setup and different pieces of building on the different steps that try to explain in this notebook how these different plotting packages work and the pieces that are needed to set this up. But once you get everything set up, as you can see, there's some pretty cool, powerful things that you can do with these different plots. I'm going to skip over how to create this interactive HTML file here. There's also information in here about, let's see, linking streams. I think we're going to just go ahead and execute some of these because I know we only have a few minutes left. And I apologize that we won't be able to get through these, but again, some of these need to build off of themselves as you continue to move through this. And I want to show you the data shader part here at the bottom. One thing in this, in the linked streams here, is that if you select one of these areas in this type of link stream plot, it will actually show up on the right-hand side here with those points that you highlighted, and it will, if you tell it to compute something for you, it can do a label where it actually computes something. So here it's computing the mean G minus R and G minus I colors for the points that you selected in the plot on the left. You can also, if you have something selected here, you can tell it to tell you how many objects were in that selected region. So there's almost 18,000 points in this selected region right here as well. Okay, so data shader is one of these things that allows you to render lots of different, very large data sets very adaptively and quickly. So if we set up another scatter plot similar to how we've been doing things before, here we're actually separating out all of the different objects in the different subpopulations as well. that, let's see, we're going to scroll down a little bit. Um, if we, let's see, which are these pieces that we want to actually get through? Okay, so if we do another color plot here where we're going to do our linked streams and we're going to apply a data shader, which means that as I'm just going to execute a bunch of cells here to try to get through this. Okay, so this is showing us another color plot with the data shader actually applied that allows you, just to illustrate quickly here, that as you zoom in and out on this plot, you can actually see uh, the overplotting here, the shading of the data that's a very dense region that's overplotted, dynamically changing as you zoom in and out on a section. And so this is what the data shader will do. It will show you how overplotted your data is, and it adapts very quickly and easily as you're zooming in and out, looking at different parts of your data. Here we're still using just the 20,000 MBAs. If you want to plot millions of data points at once, down here, it's the same example, but using our full unique MBAs data table. We'll just run these cells as well. Now we have all 4.25 million objects in here with the data shader applied here. So you can see how overplotted these points are. And again, as you zoom in and out, you can see that the shading of these points for showing the overplotting is changing very dynamically and interactively as you go along and as you zoom in. So this is kind of the power of the data shader plotting library here, of being able to quickly adapt in your plot to show you how overplotted your data actually is. Okay, so I realize we are now at the top of the hour. There's a couple additional things in here with some additional exercises for the learner at the end here. I know this was a lot of information that I threw at you trying to get through this very dense notebook. I hope I didn't lose people too much along the way. But this notebook is here. It's available to play around with. Please try to pick it apart and understand all of the different pieces. Another really great resource, as I said, is looking at the notebook that Leanne had put together. That was the DP0.2 06B notebook as well. There's additional examples in there of some of the things that these plotting libraries can do. And there's also one, the 06A notebook for DP0.2 is using these plotting libraries for doing interactive visualizations with the images on top of the catalogs as well. All we have for DP0.3 are the catalogs, not the images, but we'll try to put together a version of this for the images for solar system objects as well, once we potentially have some images for solar system objects too. So lots of great resources. If anybody has any questions, I'm happy to stay on a little bit longer and answer them now if you want. Or as you go through this, if you have questions, please post them on the community forum as well. You can directly tag me in those posts and I will answer your questions on there as well. So, all right. Thank you so much, everyone.
That was amazing.
Thank you.
That was great, Sarah. That's going to really complement Leanne's work, and I'm going to be using it. So, and the documentation is really good. I have a couple of questions.
Okay. Yeah, great.
You didn't incorporate the Y band. Is that not going to be very important for asteroids?
Yeah, I didn't incorporate wideband. I think there might not, maybe I'm wrong. I think there might not be any wideband data in the DP0.3 tables.
Okay.
I think it's not included in the
You're right.
tables. So
Mhm.
that's part of the reason why I think it's not as commonly used in general either for asteroids. But once we have real data and it's actually included in the tables, then it's absolutely something that could be used as well.
Thank you. My other question is the dynamical regions. do they vary in, do they vary at all in composition and size? You know, besides just the dynamical difference?
Yeah, so the dynamical difference, the classification I used was very simplified with just some major axis cuts.
Mhm.
To be more correct, there's cuts in inclination and things as well. But for this purposes, I just use some major axis. But yes, as you move through the main belt from the inner belt to the middle belt to the outer belt, the compositions for main belt asteroids uh, does change as you go for which compositional type of objects dominate within the different parts of the main belt as well. And so there is a little bit of a difference for the composition. The size, I don't think is very dependent on where you are at within the main belt. I think it's pretty consistent across the whole main belt. The Hungarias and the Sibiles, which are smaller families kind of on the inner and outer edge of the main belt, may have slightly different size distributions because they have smaller numbers of objects in them. But in general, it's mostly the composition that we see a bit of a change in as you go across the main belt.
Thanks.
Yeah. Let's see. Okay, any other questions from anybody? Thanks for the comment, Katie, in the chat. Okay, well, if there are no other questions, then we'll go ahead and end here. And thank you all so much for coming. And please come to, we're going to have a break for the next 3 weeks. And then on the 9th of January, Yumi will be going through the user uploaded tables in the RSP. And then on the 23rd of January is when Melissa is going to be doing the review of DP0 and the big thank you to all of the delegates. And then the following tutorial after that will be on February 6th, where we're going to be looking toward data preview 1 as well. So more interesting, exciting things to come as things are continuing to happen. So please come to those upcoming science assemblies as well. And in between each, we'll still have our drop-in Q&A session. So please always feel free to come to those as well if you have questions about anything you're working on or any of the tutorials that we have too. So thank you
very
so much.
much, Sarah.
Bye, everyone.